Quadratic functions have a particular word in it, quad, the prefix. And so when we call it its function name, it is a quadratic. Now that prefix, quad, means 4. So what's going to happen here in this function, we're going to be looking at rectangles. Rectangles are 4-sided, i.e. the quadratic formula. And we'll be looking at these 4 sides and assigning them maybe some variable representation, such as x plus 4 and x plus 3. When we look at a quadratic, however, its formula, its function, is ax squared plus bx plus c. You don't see a power of 4, you actually see a power of 2. Why is that? Well, if I'm looking at the area of this quadratic, this quadrilateral, and I multiply to find area, there's a method we're going to use called FOIL. And FOIL is just kind of like a little mnemonic device. It tells you multiply the first terms. It's a way of distributing. X times x is x squared. Outer terms for the O, inner terms, combining, and then last terms, 4 times 3 is 12. So if you notice, this 4-sided figure then has this power of 2 when I multiply that. So quadratic is going to have a power of 2. Again, quadratic is the name of the function. Once again, the form that we wrote above, it's going to be the form ax squared plus bx plus c, where a, b, and c are values. They're what we call coefficients. The shape of the graph, when I was to put it on a coordinate system, is going to give me this name called a parabola. So the parabola is the shape or the name of the graph that's coming from the quadratic. And we're going to be really interested in these new types of functions because we've all just been studying linear functions for the most part. These new functions have this U shape, parabolic shape, and they might open downward and they might open upward. We're going to be interested in these because they're going to have a max or a min. So taking a look at the graph, the lowest point here would be the minimum. Highest point here would be the maximum. And this point is called the vertex. The vertex is this high or low point on the quadratic graph called the parabola. In addition to the vertex, there's another point that we might want to just discuss here for a moment. The vertex here would be a minimum. There's going to be a point inside this called the focal point. And the focal point is just that. It focuses things. And so if this was some sort of solar heater, all the heat, because things that come in bounce off, they're going to bounce through this point called the focal point. It would be the concentration of maybe light, like in a flashlight, or heat if it was a solar cooker reflecting the sunlight. Symmetry. This graph is symmetric. If you take a look about what symmetry means, it's just going to be a mirror image. So looking at a parabola, it's symmetric, whether it open upward or downward, through the vertex. If this was a line that I was folding upon, those two parts of the parabola would line up on each other, and that's the line of symmetry. And notice it goes through the vertex. The A value, looking back at my general form of a quadratic, standard form is what it's sometimes referred to. The A value is this first coefficient. The A value is on x squared. And this A value is going to tell me the direction in which my parabola is going to open. And when we look at things with the parabola, we have to kind of just think logically. Let's see, if my A is positive, positives are up or down. So this is going to be this concave up. It's going to open upward. If my A is negative, I'm going to be what we call concave down, and it's going to open downward. In addition to a vertex, axis of symmetry, and this value telling me if it's concave up or down, we want to be able to locate the y-intercepts. And the neat thing about a parabola is a parabola always has a y-intercept. Now, if you recall a y-intercept, it happens when my x value is 0. So in other words, in function notation, I'm plugging 0 in for my x values. On a graph, it's just where that graph is going to pass through the y-axis. Notice it's going to hit it once. If I was to open downward at some point, it would hit it. So I'm always going to have this y-intercept. The x-intercept is where my graph hits the x-axis. And we actually have a couple names for where my parabola crosses the x-axis. We call those zeros, sometimes roots, sometimes solutions. And what happens here is where my function or my y-coordinate is equal to 0. So to locate these, we'll actually have 3 scenarios that we'll be looking at for the x-intercepts on my graph. One scenario might be that my graph intersects the x-axis twice. Another scenario might be my graph intersects my x-axis only once. We might even have a third scenario where my graph actually never intersects my x-axis. Still has that shape, but it's not hitting that x-axis. Why might we be looking at parabolas or quadratics? Several things in the real world follow this shape, and one common one is what we call a projectile. I shoot something up, it peaks due to gravity, gravity turns it around. And if we look at this, this is my vertex, so I can see if this is time in seconds and this is feet. I can see that after 6 seconds I reach the max of 36 feet. I can also see where it's going to hit my axes, and it looks like it hits at 0 seconds, and it hits at this point here, which is 12 seconds. How do I know that? Well, I could have counted, but I also see it's symmetric. If it takes something 6 seconds to reach the top, it's going to take the same amount of time to come down. Now, another neat thing about this quadratic or parabola, something happens right here with my slope, my rate of change. Notice if it's fired up, the rate of change is fairly steep with these little tiny slopes here, and it starts to level off. And right at the peak, my slope is horizontal, meaning my slope is equal to 0. Then my slope speeds up, it goes the other direction. And that is all due to the idea of gravity.